Hello and welcome back. So today I want to talk about transmitting information in the form of electrical signals from point A to point B using a couple wires. There seem to be quite a lot of ways to do that. I mean, you could use just two wires separated by whatever distance, you could use two wires that are coupled together, you could use twisted wires, you can use coaxial wire, you can use two wires with an extra shield around them. There seem to be quite a lot of options. So what's the difference and which one should you choose depending on your exact application? Well, if you're curious, then keep watching. So today I want to look at noise immunity. How the structure of your cable influences its immunity to electromagnetic interference, and what sort of techniques can be used to get uncorrupted data down the line. And to start things off, we need to look at how noise gets into the cable in the first place. And for that, I'll be using the worst setup possible. That being two cables separated by whatever distance, and I'll be connecting this directly to the oscilloscope on one end, and on the other my signal source is, well, a 1 kilo ohm resistor, which is giving me no signal. So I should be measuring absolutely nothing when I connect this to the measurement equipment. But what do we get? Let's see what happens. Now, even without trying, we can see that the setup, the two wires separated, is picking up quite a lot of noise from the environment. So I don't even have to do anything to induce any noise into these wires. They're doing a really good job of picking things up from around me. And what we can also notice is that the wires are sensitive to electrically conductive objects in their vicinity. So if I put my electrically conductive hand on one of the wires, well, we can see that the noise starts to become even worse than it used to be. Now, the actual test that I wanted to perform today was to induce some magnetic fields and electrical fields in a controlled manner into the wires. And for that, of course, I want to use on one side the electrical field cell that I built a while back, and also my Helmholtz coil. Both of these I prepared for an older video for my near field probe experiments. Let's take these one at a time, see what happens. So first off, with the magnetic fields, I've connected my signal generator to the second channel of the oscilloscope, and that is connected to the coils to create magnetic fields at around 100 kHz. Now, if I take my wires and bring them into the magnetic fields, we see that we're inducing a nice clear voltage into them. And depending on how closely together the wires are or how far apart, more or less voltage is being induced. At the same time, even if they are widely separated, if I change their angle, again, the amount of signal being induced changes. So now let's look at the electrical fields. So now if I take my two wires into the cell, again we can see that they are picking up some signal. And again, it depends on how the wires are laid out in the cell. So the closer they are to the live wire, so the middle electrode, the stronger the signal is. And again, depending on which of the wires is closer to this middle electrode, stronger or a weaker signal will be induced. So now, just to be clear on what's going on, let's look at this test setup on a whiteboard. Let's look at how our setup would interact with the magnetic and an electrical field. So first of all, we can consider our two wires in a uniform magnetic field, and basically what these wires look like is an inductor. So we have a single turn coil, which based on its orientation in the magnetic field, will absorb more or less of the field. So if the coil is perpendicular to the magnetic field, it's absorbing the maximum amount of energy. If it's parallel to the magnetic field, it doesn't absorb anything. Also, depending on the distance between the two lines, the bigger the distance, the bigger the inductance, so the more energy it will absorb. That's why it was helping to reduce the distance between the two wires. Now, if we would look at a different setup, say a twisted wire, in the same magnetic field, one of the interesting things that appears is the way in which current is induced. So with our first setup, depending on the direction of the magnetic field, you would have a certain direction of current being induced. Now if we look at our twisted wire, current is always induced into the same direction if it's caused by the same magnetic field, but because of the twist in the wires, the currents induced in two of these loops are opposing. So one time it's induced directly into the ground line, one time it's induced directly into the signal line. So the two currents cancel out. Basically, from a magnetic immunity point of view, this sort of twisted wire is much better at withstanding magnetic fields than the two parallel lines because of the twists and the way in which they absorb the fields. Now in real life, of course, you won't have an exact even number of these loops and they won't all be in the same uniform magnetic field, so this cancelling out effect isn't perfect, but the point is it's much better than just to have two parallel lines. Final thing to look at is if we would use shielded cable, so say a coaxial cable or some other form of shielded cable. First of all, you have the shielding around your signal line, which acts as a turn that absorbs part of the magnetic field, short-circuiting it, but also we have this opposing currents effect going on. So even with the shielded line, if it's perfectly coaxial, so the two lines are equally distanced, you will have two of these small current loops which cancel each other out. So having a twisted wire is great, but having a shielded wire is even better. Now if we look at the problem from an electrical field point of view, the electric fields couple into the system capacitively. So depending on which of the two wires is closest to the noise source, the low impedance ground line or the high impedance signal line, more or less signal will be induced into the system. So of course if the signal line is closest to the noise source, then more signal will be induced. Now if we consider a twisted line, well, that's not really helpful, because you will be inducing noise both into the signal line and into the ground line. So no matter what you do, you will get noise, regardless of the orientation. Finally, if we consider the shielded cable, well, we have an advantage here, because no matter what you do, the line exposed to the noise will be the ground line, so the low impedance ground signal. Your high impedance signal line will always be protected by the shielding. So both from a magnetic field point of view and an electrical field point of view, if we analyze immunity, the shielded cable seems to be the best option. Now, there's one more thing that's worth mentioning regarding twisted cable, and that is when we talk about differential signal lines. So what I have here is a signal source that has the same impedance on both of the lines. So none of the lines are connected to ground. If we expose this sort of system to an electrical field, then we will be getting the same amount of noise in both of the lines. Since they have the same impedance, they will absorb the same amount of noise. But because we're using a differential input stage on the other end, the noise that's induced into the lines is equally induced into both of the lines. So when we subtract the two signals, then we're left with only the useful signal. So whenever you're using a differential signal system, twisted cable is good enough because it handles both the electrical field immunity and the magnetic field immunity. So depending on the type of signaling, single-ended or differential, you might want to go for shielded cable or twisted pair cable. So now, just to make sure that reality actually fits to our theories, I got this setup in which I swapped my initial cable with this shielded cable, and I have the same 1 kilo ohm resistor on the end of it. And let's see how this thing behaves with our magnetic and electric field noise generators. So if I run this thing through my magnetic fields, well, we can't see anything. There's absolutely nothing being visible. But if we zoom in, I mean, there's still a bit of noise here and there, but nothing seems to be coming from my magnetic field coils. Now, if I increase the field strength a bit, well, you can almost make out a bit of signal being induced, but that's not really being induced into the cable as much as it's being induced into this open end. If I plug that into the coils, then we instantly see a response. So basically, as long as the shielded part is exposed to the magnetic fields, nothing really happens. So now let's move on and see how this behaves with electric fields. So now if we take our cable, put it into the electric field cell, again not much really happens. So there doesn't seem to be any sort of voltage being induced, other than if I plug in my open end, which is not shielded. So as long as there's shielding around our high impedance signal line, shielding connected to ground, it seems that the line is perfectly immune to any sort of noise. But is it? Now there's one more experiment I want to show you, and this involves using some shielded cable, so a nice coax from the oscilloscope probe, and a very large noise source generator, my power supply. Now this is a topic that I handled in a few older videos, but I just want to show this again just so we don't forget about it. Basically, my power supply isn't just noisy in a differential mode, so noise on the positive terminal in reference to the negative terminal, but also it generates quite a lot of common mode noise. Noise coming out both the supply lines and closing to protected earth. And one of the paths to close to protected earth is through the protected earth connection of the oscilloscope. So if we take our oscilloscope probe, so connect the ground to its signal pin, and we take the ground from the power supply and interconnect the two, we see a lot of noise. So by performing this interconnection, we can see the noise that's generated by the switching power supply in the power supply, and it's coupling into the oscilloscope, but not through the signal line, but rather through the shielding in the cable. So even though the shielding is providing quite a lot of protection from external magnetic and electric fields, in certain extreme cases, the shielding shows its limitations. It's not perfect. It has resistance and it has inductance. So the problem that we're getting is that the signal that reaches your input circuit, so if it's an amplifier or whatever, is not just the signal that you're sending out, but also the voltage drop that happens on your cable caused by the external interference. So these two signals get added up, and that's what reaches your end circuit. So the solution to this is to use an extra shielding layer, or in other words, separate the grounds. So what I have here is basically the same circuit as on the left side, difference being that my signal is now traveling through my shielded cable on two wires. So I have my positive signal line, but I also have my ground pin. And my shielding layer is an added on layer that only acts as a shield. This way, whatever voltage drop happens on the shielding does not get added on top of the useful signal. Now, it's worth mentioning that if you want to use a split ground concept, all the grounds need to be, first of all, interconnected. So just because you call it ground doesn't mean it is ground. And secondly, you should use a single interconnection, so not to create loops, because one of the things that you could do is connect the ground on the bottom side, but also on the top side. And then this extra ground line is basically short-circuited by the external shield, so it's not doing anything. Point being, this will only work if you use it right. Now, using an extra shielding layer is quite a common technique. You'll see it in high-quality audio cables, for example in microphone cables, but you will also see it in digital signaling systems. So for example, USB cable usually has a shielding layer, but also things like long Ethernet cables. Now, using this extra shielding layer can have different purposes. It can either be used to increase noise immunity, so to protect the signal lines from whatever noise is in the environment, but you can also use it the other way around, to reduce emissions. Your signal wires might be noisy and you don't want all that noise to go out, so you add this thing. Now, depending on your system requirements, you might need a special shielded cable, or you could get away with simple twisted wire. It all depends on just how much added noise you can accept on top of your useful signal. But for now, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye.